Hello, hello. We are now into the third podcast of week 10. Now, guys, I'm going to actually split this podcast into two. So the next topic will be podcast 3 and 4, or 3A and 3B, if you will. And similarly to what we were talking about in the previous one, is strong and weak. But in this scenario, we're talking about strong and weak bases instead of strong and weak acids. And because those weak bases will once again be in an equilibrium situation, we will have equilibrium laws, which leads itself into a base ionization constant. So let's get right into it, because we'll be able to flow a little bit faster with this since we've already talked about the strong versus weak. Now, ultimately, bases are pretty well known, right? That bitter taste versus an acidic sour taste, the slippery feel versus that really corrosive feel of an acid. But ultimately, we still have a stronger base versus a weaker base. The stronger the base, the more obvious those properties will be. And in addition, we'll end up with, of course, not a lower pH, but this is a base, a higher pH. And we also end up with that scenario, similarly to with strong acids, of a greater electrical conductivity. So once again, that means more ions must be present in a strong base than are present in a weak base. That's the only way you're going to get a greater degree of conductivity. Going into this, strong bases are really easy to recognize. You don't need any special list for them in your data booklet. Ultimately, you just need to look for hydroxide. Now, what will happen is you'll end up with a metal hydroxide. So, for example, lithium hydroxide, magnesium hydroxide. You get the idea, right, guys? So, a metal with a hydroxide, sodium hydroxide, we end up with a complete 100% dissociation, dissolving dissociation. Get used to those words again. They're all Chem 20 words. It does it to 100% quantitative degree. Thus, it is a very strong base. For instance, let's take the, what's it doing here? Here we go. This scenario of sodium hydroxide. Without a doubt, a metal hydroxide. If we start with an initial concentration of 0.42 moles per liter, because the dissociation is quantitative, my products end up being produced from a complete quantitative stoichiometric quantity perspective, right? So both of them are 0.42. Take note, guys, from a mole perspective, there's 1 mole of sodium hydroxide producing 1 mole of sodium ion and 1 mole of hydroxide ion. You still have to balance these dissociation equations. Hint, hint, that could certainly come into play. So that's a big deal. Now, because this is a base, we're going to first consider the pOH of this because we have hydroxide concentration already. Go through the formula, we end up with an extremely low pOH. Now, it's pOH, not pH. So a low pOH is highly basic. If we figure out the pH in turn by subtracting that pOH from 14, we have a super high pH, which once again is associated with a basic entity, which makes perfect sense for a strong base like sodium hydroxide. Now, scenario-wise, when you're given questions and examples, this is another thing you need to take the time to look at. If we have a strong base, then you can assume 100% dissociation, which makes the number crunching and the calculating that much easier, right? There's not as much work that needs to be done. You don't need to deal with, for instance, an equilibrium situation. First things first, same though, take the time to draw a proper equation. In this scenario, we've got magnesium hydroxide, and I'll illustrate to you in a moment why it's so important to have this equation. It is a metal hydroxide, so it's going to completely 100% dissociate, and it's going to split up into its individual ions. That's what dissociation is, thinking back to Chem 20. Now, the two ions it produces, of course, are magnesium 2+ and hydroxide. But recognize something here, guys. I have two hydroxides that are reacting and or dissociating, which means I have to have 2 hydroxides being produced. That's a huge deal. It is not a 1-to-1 ratio between the magnesium hydroxide and the hydroxide ions. Big deal. Big deal. Huge. Okay, let's keep going. How are we going to get to pH? Well, eventually we're going to need hydronium concentration. That's the only way it'll work out. Or subtract from 14. That'll be good too. How are we going to do that? Let's begin by getting the hydroxide concentration. Once you got hydroxide, you can get everything else. You can get POH, you can get pH, you can get hydronium concentration. They're also interrelated. It's super doable. Go back to the given info. Mass of magnesium hydroxide is 0.45 grams, as given in the question. From your periodic table, molar mass is 58.33 grams per mole. We're also told in the question that we've got 10.0 liters of this water that it's dissolved in. So step by step, concentration is going to be number of moles over volume. I need to get the number of moles to start. Easy to do with the mass and the molar mass. N is equal to little m over big M, 0.45 grams over that 58.33 grams per mole. Remember, guys, no rounding. Just keep your full values so that you can have as accurate of numbers going through this process as you can. 0.0077147 ... moles. Okay, there's our N. Let's go through this now and get the concentration. C is equal to, of course, N over V, which is 0.0077 ... moles over the 10 liters given to you in the question. Concentration of the magnesium hydroxide is 7.7147 ... times 10 to the negative 4 moles per liter. All right, guys, you need to use the mole ratio to relate this to hydroxide, right? This is the concentration of the magnesium hydroxide. To relate it all the way over here to hydroxide, use the mole ratio. I get pretty lazy about this. I divide by 1 because the coefficient on magnesium hydroxide is 1. Then I times by 2 moles because the coefficient on hydroxide is 2. I'm going to end up with a hydroxide concentration, I'm not going to round it yet, of 7.7147 ... times 10 to the negative 4 moles per liter. Now, nothing in the question actually asks for hydroxide concentration, but this is going to be the stepping stone to getting pH. I'll show you the way I would go about this. You might do it a different way, that's fine. For example, maybe you'll use the autoionization of water to go from there. Your choice. The end goal is the same though, pH. So if I start with then hydroxide concentration and then calculate POH, and that's the road I'm going to take, negative log of the hydroxide concentration. Plug in what I just got, negative log 7. I'm just looking at this and I realized that I number crunched wrong. Oh, that's super annoying. Oh, sorry guys. So I'm pulling out my calculator now because I can see that I'm going to have to fix the notes here. Sorry, 58.33. There we got that divided by 10. I need to take that and times it by 2. Okay, let me revamp this slightly. La la la. Going back, when you multiply this by 2, you're going to get 0.0015429 ... moles per liter. There we go. Sorry about that. Okay, so plug this in to the concentration of hydroxide. We're going to have 0.00154 ... moles per liter. Negative log of that answer. And we end up with a POH equal to 2 point, again, I'm not going to round this yet, 81164 ... Now the route I would go from this now, and I love this trick, I find it super, super helpful, is that pH and POH added together equal 14. It's really, really useful. So that means I can take 14 and subtract from it the POH that we just got, in order to get the pH. Beautiful, like really, really nice and easy. Do that. pH is equal to 14.00 minus the 2.811 dot, dot, dot. And we end up with a pH equal to 11.19. 2 sig digs, guys. Remember, only the 1 and 9 are significant. The 11 is not. And there you have it, the wonderful pH of this circumstance of magnesium hydroxide. There we go. Okay, so remember, that was for a strong base. What if we start to twist this around a little bit and we work into a weak base? Now, generally speaking, with most of our weak bases, we're going to see anions, which are negatively charged ions. They still, when they react with water, produce hydroxide, but it is not quantitative. This is an equilibrium system. Now, take note, guys, there's another typical weak base where you end up with nitrogen and oxygen. For example, if you think back to last year, ammonia was a classic one of these, right? Ammonia would gain a hydrogen to become ammonium, NH4 plus. So if you ever have a question where you're seeing some combination of N and H, like for example, you might see something like C2H6NH, something weird like that, NH2, and it'll react with water. If you see something like that, that's still going to be a weak base, but it's going to gain an extra hydrogen to become C2H6NH3 plus, right? Just hint, hint, be aware. You're going to see some weird stuff like that. Okay, let's go back to the question at hand though. Weak base scenario. So with a weak base, these will ionize in water, right? So this is not just a dissociation. The hydrogen from water, the proton in other words, is going to transfer over to the weak base. So proton transfer. That's how we end up with that HB. Now remember, water technically is HOH. So essentially what we're doing is just removing that hydrogen. When you remove that hydrogen, you end up with hydroxide, which is pretty logical. If hydroxide is produced, dun, 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 we have basic characteristics. Since this is an equilibrium situation, we can draw and write equilibrium laws, which means this is a base now. So we didn't find the acid ionization constant. It relates instead to the base ionization constant. Super logical, works into situations with a weak base. Okay. Now, let's do this example. We did a very similar one in the context of a weak acid. In this case, we have our anion, right, OCl, and this anion is going to react with water. So that weak base, OCl negative, reacts with water. When it reacts, the proton from water, just one, it's always one at a time, goes over, and we end up 2 arrows, it's equilibrium, HOCl negative, oops, sorry, not negative, HOCl aqueous, the negative plus the positive, it's at 0 now, right? -1 plus +1, 0, plus, and now this is where that hydroxide comes in, right? So OH negative. Now, equilibrium arrows means that we have initial equilibrium, changing equilibrium, and end equilibrium. What was the initial equilibrium? Well, it started with 0.10 moles per liter. Now, the whole goal of this question is to find Kb. Now, in this case, to find Kb, we're going to use a scenario, like I said, similar to what you did with that first question on weak acids, where as long as we have all of our equilibrium concentrations, we can then use those to correctly calculate Kb according to the equilibrium law. Now, this question tells you the pH, and you got to be careful. pH does not directly relate to hydroxide. pH directly relates to hydronium. Ding, ding, ding. So very, very first step here is we need to have not pH, but POH, because that relates to hydroxide. So POH is going to equal 14.00 minus 10.20. When we number crunch that, right, and the 10.00 is the pH. That's what we're subtracting. We end up with 3.80. That's the POH. Why is that a big deal? Well, if you've got the POH, then you can do step 2, and you can get the hydroxide concentration. Hydroxide is equal to our 10, come on thing here, there we go. 10 to the exponent of the negative POH equals 10 to the exponent of negative 3.80. And don't round, we're going to use this. The hydroxide concentration is equal to 1.5848 ... times 10 to the negative 4 moles per liter. Okay, why is this a big deal? Well, that is the concentration at equilibrium, because that's when we actually end up with hydroxide existing. So by finding this value now, you just found the equilibrium concentration of hydroxide, which, because they're 1 to 1, you just found the equilibrium concentration of HOCl. That's a big deal. So we can fill those in now. For the hydroxide, this is 1.58 ... times 10 to the negative 4 moles per liter. The HOCl is going to be identical. 1.58 ... times 10 to the negative 4 moles per liter. Now these both went up by X. What is X? 1.58. So they went up by 1.58 times 10 to the negative 4. So did the hydroxide. Vice versa, the OCl negative is going to go down by that same amount. So minus 1.584 ... times 10 to the negative 4 moles per liter. Subtract those two values, we get 0.0998 ... moles per liter. There we have it. All three of those values are the concentrations at equilibrium. If I know my equilibrium concentrations, I can in turn find the equilibrium constant. First step first though, write down that equilibrium law. This is a base, so Kb equals the concentration of the HOCl times the concentration of the hydroxide divided by the concentration of that weak base OCl negative. Plug in what you know. 1.584 ... times 10 to the negative 4 moles per liter. It'll be that time itself, so I'm just going to square it, makes it easier. Divided by the concentration of the anion, the OCl negative, which is 0.0998 ... moles per liter. Whew! Almost done, guys. Let's go to sig digs. According to the original values, we're going to need 2 significant digits. So when I do that, Kb is equal to 2.5 times 10 to the negative 7. No units. Equilibrium constants never have units. There you have it. We are now starting the analysis of not just strong bases, but weak bases. Okay, there's a new formula with this, and there is a new twist with it. So take a little break, absorb it, and then come back and I'll do 3B, if you will, of podcast number 3. Talk to you soon.